Two galaxies are locked in the most beautiful collision in the universe. Most people think galaxy crashes create destruction. That assumption is completely wrong. Tonight we're discovering how cosmic collisions sculpt perfection instead of chaos. Before we begin this cosmic journey, drop a comment about your favorite deep sky object. If you enjoy these galactic explorations, consider subscribing. These discoveries are meant to be shared. Charles Messier was hunting comets in 1773. A fuzzy patch kept blocking his view. He labeled it number 51 on his list and moved on. That annoying obstacle was actually a stellar metropolis. For over a century, astronomers saw cosmic fog. They called these fuzzy patches nebulae. That's just Latin for clouds. Everyone assumed they were nearby gas clouds floating in our solar system. Advanced telescopes revealed the shocking truth. That innocent haze was individual stars, hundreds of billions of them, each one a blazing nuclear furnace like our sun. The scale defies imagination. This single galaxy contains more stars than grains of sand on every beach on Earth. We'd been staring at one of the universe's largest cities while thinking it was empty space. Here's where physics breaks every rule about destruction. Two massive galaxies are colliding right now. Logic says this should create cosmic carnage. Instead, you're looking at the most elegant spiral in the known universe. The spiral arms sweep outward like frozen rivers of light. They stretch across unimaginable distances. Each arm maintains perfect structure despite billions of years of gravitational chaos. A smaller companion galaxy acts as cosmic sculptor. That small yellow blob at the edge isn't just sitting there. It's reshaping the entire main galaxy through pure gravitational force. The companion creates what astronomers call density waves. Think of ripples spreading through water when you drop a stone. These invisible waves compress gas clouds as they sweep through space. Compressed gas ignites into brilliant star formation. The galaxy glows brightest exactly where the spiral appears most defined. Gravitational chaos becomes the universe's most masterful architect. This galaxy sits in the perfect spot for Earthbound observers. Most galaxies hide in crowded star fields or lurk behind cosmic dust. The Whirlpool chose the ideal neighborhood. It lives in a constellation called Canis Venatici. That's Latin for hunting dogs. You can find it near the handle of the Big Dipper. That familiar star pattern acts like a cosmic road sign pointing straight to our target. The galaxy positioned itself in relatively empty space. No bright stars compete for attention. No dust clouds block the view. It's like having front-row seats to the universe's greatest spiral show. Amateur astronomers can spot this galaxy with small telescopes. Even modest backyard equipment reveals the spiral structure. Most deep space objects remain invisible to casual stargazers. The Whirlpool breaks that rule completely. Pure cosmic luck gives us the perfect viewing angle. Most spiral galaxies appear edge-on from Earth. They look like thin lines or narrow ovals. We miss all the spiral structure entirely. The Whirlpool faces us directly. Imagine looking down at a spinning pinwheel from above. That's exactly how we see this galaxy's spiral arms spread out in perfect symmetry. This face-on orientation reveals architectural details invisible in other galaxies. We can trace each spiral arm from the bright central core to the faint outer edges. We can see how the arms connect and where they begin to fragment. Astronomers estimate that fewer than 10% of spiral galaxies appear face-on from our perspective. Most remain tilted at awkward angles that hide their true structure. The Whirlpool won the cosmic lottery for perfect positioning. Look at any image of the Whirlpool and notice the striking color differences. The spiral arms blaze with brilliant blue light. The regions between arms glow with warm yellow tones. This isn't random decoration. It's a map of stellar evolution. Blue light reveals where massive young stars are being born. These stellar giants burn incredibly hot and bright. They live fast and die young in cosmic terms. The spiral arms concentrate these stellar nurseries like cosmic maternity wards. Yellow regions contain older, calmer stars like our Sun. These middle-aged stars have settled into steady nuclear burning. They've moved away from their birthplaces in the spiral arms. They now populate the quieter spaces between arms. This color pattern tells the galaxy's life story. New stars form in the spiral arms. They age and migrate to calmer regions. The cycle repeats endlessly. The whirlpool becomes a living timeline of stellar evolution written in light. The whirlpool spans distances that make our solar system look microscopic. Our entire solar system, from the Sun to the outermost planets, could fit into a tiny fraction of this galaxy's central region. This galaxy contains roughly the same number of stars as our own Milky Way. That means hundreds of billions of individual nuclear furnaces, each one potentially hosting its own family of planets. Imagine traveling across the whirlpool at the speed of light. Light can circle Earth 7 times in 1 second, yet crossing this galaxy would take 100,000 years even at light speed. The scale overwhelms human comprehension. If you could shrink the whirlpool to the size of a dinner plate, our entire solar system would be smaller than a single atom on that plate. This puts cosmic scale into perspective that's almost impossible to grasp. The whirlpool displays a cosmic color wheel that maps different types of stars. The central bulge glows with warm yellow and orange light. The spiral arms blaze with brilliant blue and white fire. This color separation isn't random. It reveals the galaxy's stellar demographics. Yellow light in the center comes from older stars. These are stellar senior citizens that have burned steadily for billions of years. They've settled into the galaxy's gravitational heart like retirees moving to a quiet neighborhood. Blue light in the spiral arms signals massive young stars. These stellar teenagers burn nuclear fuel at reckless rates. They outshine dozens of stars like our Sun. Their intense radiation lights up the surrounding gas clouds in spectacular displays. This color coding helps astronomers read the galaxy's history. The central yellow region formed first. The blue spiral arms represent ongoing star formation. The whirlpool shows us both its ancient past and its active present in a single image. That small yellow blob at the edge of the main spiral isn't just a background object. It's the cosmic choreographer responsible for the whirlpool's spectacular structure. This smaller galaxy, cataloged as NGC 5194, plays a crucial role in shaping its larger partner. The companion galaxy contains billions of stars of its own. It's roughly 1/10 the mass of the main whirlpool. But size doesn't matter in cosmic gravitational battles. This smaller galaxy wields enough gravitational influence to reshape its giant partner. The two galaxies orbit each other in a cosmic waltz that's been ongoing for hundreds of millions of years. Each close approach sends gravitational waves rippling through both galaxies. These waves trigger the spectacular spiral structure we see today. Without this companion, the main galaxy would look completely different. It might be a boring elliptical galaxy or a chaotic irregular shape. The companion's gravitational choreography creates the universe's most photographed spiral structure. Astronomers classify the whirlpool as an SSE-type spiral galaxy. That technical designation reveals crucial details about its structure and evolution. The classification system works like a cosmic family tree for galaxies. The S means it's a spiral galaxy with clear arms extending from a central core. The C indicates loose, open spiral arms with lots of space between them. This contrasts with tightly wound spirals that have arms wrapped close to the center. C galaxies represent about 1/4 of all spiral galaxies in the universe. They typically show active star formation in their spiral arms. They contain substantial amounts of gas and dust needed to build new stars. The Whirlpool exemplifies this galaxy type perfectly. This classification helps astronomers understand galactic evolution. C galaxies like the Whirlpool represent a specific stage in cosmic development. They're mature enough to have clear structure, but young enough to keep forming new stars. The Whirlpool democratizes deep space astronomy. While most galaxies require large professional telescopes to reveal any detail, this cosmic gem rewards even modest amateur equipment with spectacular views. A 6-inch telescope shows the spiral structure clearly on dark nights. Photography enthusiasts can capture stunning images with relatively simple camera equipment. The galaxy's brightness and high contrast make it forgiving for beginners learning astrophotography techniques. The Whirlpool appears large enough in telescopes to show real structure. Most galaxies look like fuzzy stars even in decent telescopes. This galaxy reveals actual spiral arms, bright knots of star formation, and the distinctive companion galaxy. This accessibility makes the Whirlpool a rite of passage for amateur astronomers. It's often the first spiral galaxy that stargazers see in detail. Many lifelong astronomy enthusiasts trace their passion back to their first clear view of these cosmic spiral arms. The Whirlpool holds the title as the most photographed deep space object among amateur astronomers worldwide. Online astronomy forums overflow with images of this spectacular galaxy. Every clear spring night brings dozens of new photographs from backyard observatories. Professional observatories have captured this galaxy in every wavelength of light. Radio telescopes map its invisible gas clouds. X-ray satellites reveal its hidden black holes. Infrared cameras penetrate its dust lanes. Each wavelength adds new layers to our understanding. The galaxy's perfect orientation and striking structure make it irresistible to photographers. Unlike edge-on galaxies that look like thin streaks, the Whirlpool spreads its spiral arms in full display. The contrast between bright arms and dark lanes creates naturally dramatic compositions. This galaxy launched thousands of astronomy careers. Students see textbook photos and want to capture their own version. Amateur astronomers spend years perfecting their Whirlpool images. The galaxy that started as Charles Messier's obstacle became the universe's greatest inspiration for cosmic photographers. The smaller galaxy can't win this gravitational battle. Physics makes the outcome inevitable from the start. When two galaxies with vastly different masses interact, the larger one always dominates the cosmic choreography. The main Whirlpool galaxy outweighs its companion by roughly 10-1. That's like comparing a bowling ball to a marble. The size difference determines who leads this cosmic waltz and who follows the gravitational rhythm. Mass equals gravitational authority in space. The larger galaxy's superior gravity pulls and shapes its smaller partner. The companion galaxy becomes a cosmic puppet dancing to the main galaxy's gravitational tune. This mass imbalance creates the spectacular spiral structure we see today. The smaller galaxy lacks enough gravitational muscle to significantly deform its giant partner. Instead, it acts as a cosmic stirring spoon, creating ripples that organize the main galaxy into perfect spiral patterns. The smaller galaxy traces an enormous elliptical path around its massive partner. This cosmic racetrack stretches across distances that make our solar system look microscopic. Each complete orbit requires hundreds of millions of years to finish. Elliptical orbits create a rhythm, approach and retreat. Sometimes the companion swings relatively close to the main galaxy. Other times it retreats to cosmic suburbia. This cyclical dance drives the ongoing interaction between these gravitational partners. The orbital period exceeds the entire history of complex life on Earth. Dinosaurs rose and fell during just a fraction of one complete orbit. Human civilization represents barely a cosmic blink in this galactic ballad. This extended timeline explains why the interaction continues today. These galaxies began their gravitational dance when the universe was much younger. They're still working through the slow-motion collision that started eons ago. When galaxies approach each other, differential gravity becomes a cosmic sculptor. The gravitational force varies with distance according to precise mathematical rules. Objects closer to the massive galaxy feel stronger pull than objects farther away. This differential pull stretches both galaxies like cosmic taffy. Astronomers call these forces tidal interactions, the same physics that creates ocean tides on Earth. But galactic tides operate on scales that dwarf anything we experience on our planet. Tidal forces don't just stretch the galaxies uniformly. They create complex patterns of compression and expansion throughout both cosmic structures. Gas clouds get squeezed in some regions and stretched thin in others. These tidal deformations trigger the spectacular star formation we see in the Whirlpool's spiral arms. Compressed gas reaches the critical density needed to ignite nuclear fusion. The gravitational dance becomes a stellar nursery on cosmic scales. Most of the time, these galaxies maintain a respectful cosmic distance. But when the companion reaches periapsis, that's astronomers speak for the closest point in its orbit, everything changes dramatically. During closest approach, gravitational forces reach their peak intensity. The companion galaxy's gravity creates maximum disturbance in the main galaxy structure. Stars and gas clouds experience the strongest stretching of the entire orbital cycle. These close encounters happen roughly every few 100 million years. Each passage leaves lasting marks on both galaxies' structures. The cumulative effect of multiple close approaches shaped the spectacular spiral pattern we observe today. Current observations suggest we're witnessing the aftermath of a relatively recent periapsis passage. The sharp definition of the spiral arms indicates the gravitational stirring happened within the cosmic recent past. The galaxies are still responding to their latest gravitational embrace. Stars and gas from the companion galaxy are slowly migrating toward their massive neighbor. This cosmic brain drain operates according to gravitational laws that favor the more massive object. The smaller galaxy gradually loses its outer material to its larger partner. The transfer process follows predictable patterns. Outer regions of the companion experience weaker gravitational binding to their home galaxy. When the main galaxy's gravity competes for this material, the larger galaxy usually wins. This material transfer doesn't happen all at once. Individual stars and gas clouds make the journey over millions of years. Some material gets completely captured by the main galaxy. Other material gets stretched into long streams between the two cosmic partners. The ongoing theft explains why the companion galaxy appears somewhat distorted in images. It's being slowly dismantled by the superior gravitational pull of its larger neighbor. This galactic cannibalism will continue until the companion is completely absorbed. What do you see when you stretch taffy between your hands? A thin bridge of material connects the two pieces. The same thing happens when galaxies interact gravitationally. Stars and gas form bridges spanning the cosmic gulf between these gravitational dance partners. These stellar bridges aren't solid structures like terrestrial bridges. They're streams of material flowing between the galaxies according to gravitational physics. The bridges mark the paths where tidal forces have pulled material away from both galaxies. Bridge structures provide crucial evidence for ongoing galactic interaction. Isolated galaxies don't develop these connecting streams. Only gravitationally interacting systems create the tidal tails and bridges visible in detailed images. The Whirlpool's bridge structure confirms that these galaxies are genuinely interacting, not just appearing close together by chance. The bridge acts as a cosmic fingerprint, proving these galaxies are gravitationally bound partners in an ongoing cosmic dance. You can't detect the motion just by looking at pretty pictures. These galaxies are racing through space at tremendous speeds relative to each other, but their cosmic scale orbital motion remains completely invisible to direct observation. Astronomers measure galactic velocities using the Doppler effect. This is the same physics that makes ambulance sirens pitch as they pass by. Light from approaching objects appears slightly bluer. Light from receding objects appears slightly redder. Spectroscopic measurements reveal velocity differences between different parts of both galaxies. Some regions are moving toward us while others move away. This velocity mapping proves the galaxies are orbiting each other in three-dimensional space. The relative velocities involved reach hundreds of kilometers per second. That's fast enough to circle Earth in just a few minutes. Yet the enormous distances make this motion undetectable without sophisticated instruments measuring subtle color shifts in starlight. These gravitational disturbances create cosmic traffic patterns that organize star formation. The companion galaxy's gravity doesn't just pull on individual stars and gas clouds. It creates waves of density that sweep through the main galaxy like ripples on a cosmic pond. Density waves aren't made of water. They're regions where material gets temporarily compressed as the wave passes through. Think of cars bunching up in highway traffic jams. The traffic jam moves down the highway even though individual cars don't travel at the same speed. These density waves trigger star formation as they compress gas clouds along their path. The compressed gas reaches critical density for nuclear fusion to begin. New stars light up along the wave fronts, creating the brilliant spiral arm structure we observe. The wave pattern rotates more slowly than the galaxy's material. This speed difference allows the density waves to maintain their spiral structure over cosmic time. Individual stars orbit in and out of the spiral arms, but the arm pattern itself remains stable. This gravitational bollet began when the universe was much younger than it is today. The interaction process started roughly 1 billion years ago. Earth hadn't even formed yet when these galaxies first began their cosmic courtship. The timescale involved dwarfs human comprehension. The entire history of life on Earth represents just a fraction of this ongoing galactic interaction. Dinosaurs lived and died during what amounts to cosmic moments in this extended dance. Current observations capture just one snapshot of an ongoing evolution. The spectacular spiral structure we see today didn't appear overnight. It developed gradually through countless orbital cycles and gravitational encounters. Future evolution will continue this slow-motion transformation. Computer models predict the interaction will intensify over the next several billion years. The cosmic dance that began in the distant past will continue long after our sun burns out. Supercomputers can recreate this entire gravitational dance using the laws of physics. Scientists input the masses, positions, and velocities of both galaxies. The computer calculates how gravity shapes their interaction over cosmic time. These simulations require enormous computational power. Each calculation tracks the gravitational influence of millions of individual particles representing stars and gas clouds. The computers must follow these interactions through billions of years of cosmic evolution. Numerical simulations reveal details impossible to observe directly. They show how the spiral structure evolved from the galaxy's first encounter. They predict how the interaction will continue into the cosmic future. The simulated results match observations of the real whirlpool remarkably well. This agreement proves that scientists understand the physics governing galactic interactions. Gravity alone can explain the spectacular structure we see through our telescopes today. What if the spiral arms aren't actually made of permanent material? This revolutionary idea changed how astronomers understand galaxy structure. The spiral arms we see aren't fixed collections of stars and gas. They're temporary traffic jams in the cosmic flow. Density waves work like phantom patterns moving through the galaxy. Imagine cars bunching up at a construction zone on the highway. The traffic jam moves along the road even though individual cars eventually drive through and continue their journey. The spiral pattern rotates through the galaxy like a slow-motion wave. Stars and gas clouds flow into the arms, get compressed briefly, then flow back out. The arms remain visible because compressed material shines brighter than the surrounding regions. This wave theory solves a major puzzle in galactic astronomy. Without density waves, spiral arms would wind up and disappear within a few rotations. The wave pattern maintains spiral structure across billions of years of galactic evolution. Galaxies don't rotate like solid wheels. Different regions spin at different speeds, creating a cosmic version of a warped record player. This differential rotation should destroy spiral patterns almost immediately. Stars near the galactic center complete orbits much faster than stars in the outer regions. If spiral arms were made of permanent material, this speed difference would wind them into tight coils within just a few rotation cycles. The inner regions rotate faster because they feel stronger gravitational pull from the galaxy's central mass. Outer regions rotate more slowly because they're farther from the gravitational center. This creates shear forces throughout the galactic disk. Differential rotation provides the energy source for creating and maintaining spiral patterns. The speed differences generate instabilities that organize into the beautiful spiral structures we observe. What seems like it should destroy spirals actually creates them. You can't create perfect art without the right tools. The companion galaxy serves as the universe's most precise sculpting instrument. Its gravitational influence doesn't destroy the main galaxy's structure. It refines it into cosmic perfection. The companion's gravity creates periodic disturbances as it orbits the main galaxy. Each close approach sends gravitational ripples, propagating through the larger galaxy's disk. These ripples organize random motions into coherent spiral patterns. Small gravitational nudges produce enormous structural changes over cosmic time. The companion doesn't need to be massive to reshape its larger partner. Persistent, rhythmic gravitational influence creates cumulative effects that transform the entire galactic architecture. Without the companion's sculpting influence, the main galaxy would likely display much weaker spiral structure. Many isolated galaxies show irregular or chaotic patterns. The Whirlpool's spectacular symmetry results directly from its gravitational partnership. Resonance happens when two rhythms match perfectly. Musical instruments use resonance to amplify sound. Galaxies use resonance to amplify spiral structure. At specific distances from the galactic center, orbital periods synchronize with the spiral pattern's rotation. These resonance zones act like cosmic amplifiers for spiral waves. Material orbiting at resonance locations gets repeatedly nudged by the passing spiral pattern. Each nudge reinforces the wave, making the spiral structure stronger and more persistent. Different types of resonance create different effects throughout the galaxy. Inner resonances can trap material and create central bars. Outer resonances can terminate spiral arms or launch material into intergalactic space. The companion galaxy fine-tunes these resonance locations by modifying the gravitational field. Its influence determines where resonances occur and how strongly they affect the spiral structure. Resonance zones become the backbone supporting the galaxy's architectural framework. When density waves move through galactic gas, they don't just create gentle compressions. They generate shock fronts, walls of compressed gas moving through space at tremendous speeds. These cosmic shock waves trigger the spectacular star formation visible in spiral arms. Shock waves form when the density wave moves faster than sound can travel through the galactic gas. The gas can't get out of the way fast enough, so it piles up like snow in front of a snowplow. This creates regions of extremely compressed material. Compressed gas reaches the critical density needed to trigger gravitational collapse. Individual gas clouds within the shock front begin collapsing under their own gravity. Nuclear fusion ignites in the densest regions, creating newborn stars. The shockwave structure explains why spiral arms appear so bright. They're not just collections of existing stars. They're active star formation regions. The spiral pattern creates an ongoing conveyor belt of stellar nurseries throughout the galactic disk. Spiral patterns have their own rotation speed, separate from the material moving through them. This pattern speed determines whether spiral structure can survive over cosmic time. Too fast or too slow, and the spirals would either wind up too tightly or fade away completely. The pattern rotates more slowly than most of the galactic material. This speed difference allows stars and gas to flow through the spiral arms rather than getting permanently trapped. Material enters an arm, gets compressed, then exits on the other side. Pattern speed is precisely tuned by the galaxy's mass distribution and the companion's gravitational influence. The companion's orbital characteristics determine the dominant pattern speed throughout the galactic disk. This external pacing prevents the spiral from self-destructing. Observations confirm that the Whirlpool's spiral pattern rotates at exactly the right speed to maintain long-term stability. The pattern has persisted for hundreds of millions of years because its rotation rate matches the galaxy's underlying gravitational structure. Galaxies contain vast magnetic fields that most people never think about. These invisible force fields stretch across thousands of light years, organizing the flow of gas and cosmic rays throughout the galactic disk. In spiral galaxies, magnetic fields align themselves with the spiral structure. Magnetic fields don't just passively follow the spiral pattern. They help create and maintain it. Moving gas drags the magnetic field lines along, while the magnetic forces influence how gas flows through the galaxy. This creates a feedback loop that reinforces spiral structure. The magnetic field acts like cosmic rebar, reinforcing the spiral arm's structural integrity. Gas flowing along magnetic field lines encounters less resistance than gas trying to cross field lines. This channels material flow along the spiral pattern. Magnetic field alignment provides an additional stabilizing mechanism for spiral structure. Even when gravitational disturbances try to disrupt the pattern, magnetic forces help restore spiral organization. The invisible magnetic scaffold supports the visible spiral architecture. Look at any spiral galaxy and notice how tightly wound its arms appear. This winding angle, called the pitch angle, reveals crucial information about the galaxy's internal gravitational structure. Tightly wound spirals have small pitch angles. Loosely wound spirals have large pitch angles. The Whirlpool displays a relatively open spiral pattern with a moderate pitch angle. This indicates a specific balance between gravitational forces, rotation speed, and external influences. Different galaxies with different pitch angles have different internal physics. Pitch angle depends on the galaxy's mass distribution and rotation curve. Galaxies with more centrally concentrated mass tend to have tighter spirals. Galaxies with flatter rotation curves tend to have more open spiral patterns. The companion galaxy's influence modifies the main galaxy's natural pitch angle, without the gravitational perturbation from its smaller partner. The Whirlpool might display a completely different spiral geometry. The observed pitch angle reflects the ongoing gravitational interaction. Early astronomers faced a devastating puzzle about spiral galaxies. Simple calculations showed that spiral arms should wind themselves into tight knots within just a few 100 million years. This winding problem threatened to invalidate the entire concept of long-lived spiral structure. Differential rotation creates the winding problem. Inner regions of galaxies orbit faster than outer regions. If spiral arms were permanent features, this speed difference would wrap them around the galactic center like thread on a spool. The timescale for complete winding is much shorter than the age of galaxies. Spiral galaxies should have wound themselves into unrecognizable tangles billions of years ago. Yet we observe spectacular spiral structure throughout the universe today. Density wave theory solved the winding problem by showing that spiral arms aren't permanent material features. They're transient patterns that can maintain their shape even as individual stars and gas clouds move through them. The pattern persists while the material flows. Most spiral galaxies display messy, irregular arm patterns with multiple fragments and branches. The Whirlpool belongs to a special class called grand design spirals. These galaxies show just two major arms extending symmetrically from the central region. Grand design spirals require special conditions to form and maintain their elegant symmetry. The gravitational field must be precisely organized to support a two-armed pattern. Random disturbances would quickly break the symmetry and create more chaotic structures. Binary galaxy interactions commonly trigger grand design spiral patterns. The companion galaxy's gravitational influence organizes the main galaxy's structure into symmetric, two-armed geometry. Isolated galaxies rarely display such perfect spiral architecture. The Whirlpool's grand design structure proves that its interaction with the companion galaxy is ongoing and dynamically important. The spectacular two-armed pattern we observe today results directly from billions of years of gravitational choreography between cosmic dance partners. Two astronomers named Lin and Xu developed the mathematical framework that finally explained how spiral galaxies work. Their theory treats spiral arms as quasi-steady density waves propagating through the galactic disk. This mathematical model became the foundation for modern understanding of spiral structure. Lin-Xu theory describes spiral arms as self-sustaining wave patterns. The waves maintain their shape by extracting energy from the galaxy's rotation. This creates a feedback mechanism that can support spiral structure over cosmic time periods. The theory predicts specific relationships between spiral arm characteristics and galactic properties. Observations of real galaxies confirm many of these mathematical predictions. The agreement between theory and observation validates our understanding of spiral galaxy physics. Modern computer simulations based on Lin-Shu theory can reproduce the detailed structure of galaxies like the Whirlpool. The mathematical framework provides the physical foundation for understanding how gravitational interactions create and maintain cosmic spiral architecture. Remove the companion galaxy and everything changes. Computer simulations show that the main galaxy's spectacular spiral structure depends critically on its gravitational interaction with the smaller partner. Without this cosmic choreographer, the Whirlpool would look completely different. Isolated galaxies rarely display the sharp, symmetric spiral patterns we see in the Whirlpool. Most develop irregular or weakly defined arms. Some become featureless elliptical galaxies. The companion's influence is essential for maintaining spectacular spiral architecture. The interaction amplifies spiral wave modes that would otherwise fade away. Without periodic gravitational stirring, the density waves would lose energy and dissipate. The companion acts as a cosmic engine driving the spiral pattern. Future observations may reveal what happens when the interaction finally ends. As the companion galaxy gets absorbed, the spectacular spiral structure will likely fade. The universe's most photographed galaxy owes its beauty to an ongoing gravitational partnership that won't last forever. Cold gas clouds drift peacefully through space for millions of years. Then density waves arrive like cosmic bulldozers. These invisible gravitational waves compress the gas until something remarkable happens. Nuclear fusion ignites. The compression process follows predictable physics. Gas clouds need to reach a critical density before gravity can trigger star formation. Most of the time, gas remains too thin and cold to collapse under its own weight. Density waves provide the extra gravitational push needed to cross this threshold. As the wave passes through a gas cloud, it compresses the material like squeezing a sponge. The compressed gas reaches the critical density for gravitational collapse. Once collapse begins, the process accelerates rapidly. Gravity pulls material inward while nuclear reactions heat the core. Within a few million years, a cold gas cloud transforms into a blazing nuclear furnace. The Whirlpool's spiral arms mark exactly where this compression mechanism operates most effectively. Why do some regions of the Whirlpool glow with distinctive pink light? This rosy illumination comes from hydrogen gas heated by newborn stars. Astronomers call these glowing regions H2 regions. That's scientific notation for ionized hydrogen. Massive young stars burn nuclear fuel at incredible rates. Their surface temperatures reach tens of thousands of degrees. This extreme heat produces intense ultraviolet radiation that can strip electrons from nearby hydrogen atoms. Stripped hydrogen atoms eventually recapture their electrons. When electrons reunite with hydrogen nuclei, they emit specific colors of light. The most prominent emission appears as deep pink or red light that makes stellar nurseries glow like cosmic neon signs. H2 regions trace the locations of recent star formation throughout the galaxy. The pink glow reveals where density waves have successfully compressed gas clouds into stellar nurseries. These cosmic maternity wards mark the spiral arms with distinctive rosy light. Massive blue stars don't live alone. They form exclusive cosmic neighborhoods. Astronomers call these stellar communities OB associations. The O and B refer to the hottest, most massive types of stars known to astronomy. These stellar giants outweigh our Sun by factors of 10 to 100. Their nuclear furnaces burn so intensely they appear brilliant blue or blue-white. They consume their nuclear fuel at reckless rates and live only a few million years. OB associations concentrate along the spiral arms because that's where star formation happens most actively. The density wave compression mechanism preferentially creates massive stars in these regions. Lower mass stars form throughout the galaxy, but the massive giants cluster in spiral arms. The brilliant blue light from OB associations makes spiral arms visible from enormous distances. Without these massive stellar beacons, spiral structure would be nearly impossible to detect in distant galaxies. The blue giants serve as cosmic lighthouse networks marking galactic architecture. The Whirlpool produces new stars at nearly 10 times the rate of isolated galaxies. This stellar baby boom results directly from the ongoing gravitational interaction with its companion galaxy. Galactic collisions don't just create pretty spirals. They supercharge star formation. Isolated galaxies form stars at steady, predictable rates determined by their gas content and internal structure. The Whirlpool breaks this pattern completely. Its star formation rate exceeds what astronomers would predict based on available gas alone. The companion galaxy's gravitational influence triggers enhanced compression throughout the main galaxy's disk. More compression events mean more gas clouds reach the critical density for star formation. The interaction creates a stellar production line operating in overdrive. This enhanced star formation won't continue indefinitely. Eventually, the galaxies will consume their available gas supply or the interaction will weaken. But currently, we're witnessing a cosmic star formation explosion triggered by gravitational dynamics. You can't see the raw materials for star formation with ordinary telescopes. The coldest, densest gas clouds in galaxies remain completely invisible to optical observation. These molecular clouds contain the hydrogen molecules that eventually become new stars. Molecular hydrogen forms only in extremely cold environments. Temperatures must drop to just a few degrees above absolute zero. At these frigid temperatures, individual hydrogen atoms pair up to form hydrogen molecules, the basic building blocks for star formation. Molecular clouds concentrate along spiral arms because compression waves create ideal conditions for molecule formation. The waves not only compress existing gas, but also cool it to temperatures where molecules can survive and accumulate. Radio telescopes can detect molecular clouds by observing carbon monoxide, a tracer molecule that accompanies molecular hydrogen. These observations reveal vast reservoirs of star formation fuel concentrated exactly where density waves operate most effectively. Massive stars create their own destruction through spectacular supernova explosions. These cosmic bombs don't just mark the end of stellar lives. They regulate where and when new stars can form. Supernova feedback creates a self-regulating cycle of stellar birth and death. Supernova explosions release energy equivalent to billions of nuclear weapons detonating simultaneously. This energy heats surrounding gas to millions of degrees and blasts it away from star formation regions at tremendous speeds. The heated, dispersed gas becomes too hot and thin to form new stars. Supernova feedback temporarily shuts down star formation in regions where massive stars have exploded. This creates a breathing pattern in galactic star formation rates. Eventually, the dispersed gas cools and settles back into the galactic disk. The cycle begins again as density waves compress the cooled gas into new molecular clouds. Supernova feedback ensures star formation proceeds in waves rather than consuming all available gas at once. The Whirlpool displays a striking color transition from blue spiral arms to yellow interarm regions. This isn't random cosmic decoration. It's a detailed map of stellar demographics throughout the galaxy. Different colors reveal different generations of stars. Blue regions contain the youngest, most massive stars in the galaxy. These stellar teenagers live fast and die young, burning through their nuclear fuel in just a few million years. They remain concentrated near their birthplaces in the spiral arms. Yellow regions contain middle-aged stars like our Sun. These stellar adults have moved away from their original star formation sites and now populate the calmer regions between spiral arms. They burn nuclear fuel steadily for billions of years. The color gradient reveals galactic rotation in action. Stars form in blue spiral arms, age into yellow middle age, then migrate to interarm regions as they orbit the galactic center. The Whirlpool becomes a living timeline of stellar evolution written in starlight. Some areas of the Whirlpool produce stars at rates that dwarf even the enhanced galaxy-wide average. These starburst regions represent star formation in hyperdrive, cosmic factories operating at maximum capacity. The most intense starburst activity occurs where the companion galaxy's gravitational influence reaches maximum strength. These regions experience the strongest compression waves and most efficient gas cloud collapse. Starburst regions can consume their available gas supply within just a few tens of millions of years. This represents a cosmic eye blink compared to normal galactic evolution timescales. The extreme star formation rates cannot be sustained indefinitely. Current observations capture the Whirlpool during a temporary period of enhanced activity. Future evolution will likely see star formation rates decline as the interaction weakens and available gas gets consumed. We're witnessing a brief but spectacular cosmic fireworks display. Newly formed stars don't just shine their light directly into space. Much of their ultraviolet radiation gets absorbed by cosmic dust grains surrounding the star formation regions. This absorption-remission process creates a secondary glow in infrared light. Dust grains act like cosmic solar panels, absorbing high-energy ultraviolet photons from hot young stars. The absorbed energy heats the dust grains to temperatures of several hundred degrees. The heated dust then re-emits this energy as lower-energy infrared radiation. Infrared observations reveal star formation activity hidden from optical telescopes. Dense dust clouds that completely block visible light become transparent to infrared radiation. This allows astronomers to peer inside stellar nurseries and study star formation in real time. The dust absorption and re-emission process explains why star formation regions appear bright in infrared images, but often look dark in visible light photographs. The dust simultaneously hides and reveals the stellar nurseries depending on the wavelength used for observation. Not all gas in galaxies gets converted into stars. Most galaxies operate at relatively low efficiency, converting only a small percentage of their gas supply into stellar material. The Whirlpool operates at much higher efficiency than isolated galaxies. Star formation efficiency measures how effectively a galaxy converts raw gas into finished stars. Typical galaxies achieve efficiencies of just a few percent over cosmic time. The Whirlpool achieves efficiencies several times higher than this average. The enhanced efficiency results from the companion galaxy's gravitational stirring. More frequent compression events mean more gas clouds reach the critical density for star formation. The interaction increases both the rate and efficiency of stellar production. This high efficiency can't continue indefinitely without consuming the galaxy's entire gas supply. Current models predict the enhanced star formation will gradually decline as the interaction evolves and available fuel gets depleted. New stars don't just form randomly throughout the galaxy. They trigger the formation of additional stars in nearby regions. This creates a chain reaction that spreads star formation across space like a slow-motion cosmic wildfire. Massive stars produce powerful stellar winds that sweep through surrounding space at thousands of kilometers per second. These winds compress nearby gas clouds, potentially triggering new rounds of star formation in adjacent regions. Supernova explosions create expanding shock waves that can also trigger star formation in neighboring gas clouds. The shock compression provides the extra gravitational push needed to initiate collapse in previously stable clouds. This generational cascade creates star formation complexes that span hundreds of light years across. Individual star formation events trigger multiple secondary events, creating expanding networks of stellar nurseries throughout the galactic disk. The Whirlpool's spectacular spiral structure partly results from this chain reaction amplification of star formation activity. Gas doesn't stay put in galaxies. It's constantly on the move. The companion galaxy's gravitational pull creates a cosmic conveyor belt that transports material from the outer regions toward the galactic center. This radial inflow process feeds the galaxy's central engine with fresh fuel. Radial flow means movement directly inward or outward from the center, like spokes on a bicycle wheel. Most galactic gas normally orbits in circles around the center. The gravitational interaction breaks this circular pattern and creates inward-flowing streams. The companion's gravity acts like a cosmic vacuum cleaner, gradually pulling outer material toward the main galaxy's center. Each orbital passage of the companion strengthens this inward flow. Gas that once stayed in the galactic suburbs now migrates toward the cosmic downtown. This inward migration increases the fuel supply available to the central black hole and surrounding star formation regions. The enhanced gas flow explains why interacting galaxies often display more active central regions than their isolated counterparts. Gravitational interaction becomes a cosmic logistics system. When you pull taffy apart, thin streams stretch between the separated pieces. The same thing happens when galaxies interact gravitationally. Tidal forces create long streams of stars and gas that extend far beyond the main galactic bodies into intergalactic space. These cosmic streamers form when the companion's gravity pulls material away from both galaxies' outer regions. The pulled material doesn't just disappear. It creates bridges and tails that can stretch across hundreds of thousands of light years of empty space. Tidal tails provide smoking gun evidence for ongoing galactic interactions. Isolated galaxies don't develop these extended structures. Only gravitationally interacting systems create the stretched-out streams visible in deep photographs. The Whirlpool's tidal tail marks the path of material stripped away by gravitational forces during previous close encounters. This stellar debris trail records the history of the ongoing cosmic dance between these gravitational partners. What happens when fast-moving gas clouds smash into each other at hundreds of kilometers per second? The collision converts kinetic energy into heat, raising gas temperatures to millions of degrees. This shock heating process creates some of the hottest material in the galaxy. Shock heating works like cosmic car crashes. When gas moving in different directions collides, the kinetic energy of motion gets converted into thermal energy. Heat. The faster the collision, the higher the resulting temperature. Gas heated to millions of degrees glows brightly in X-ray wavelengths. X-ray telescopes can detect these collision zones throughout interacting galaxy systems. The X-ray emission maps exactly where the most violent gas interactions occur. Shock-heated gas eventually cools and settles back into the galactic disk, but the heating process temporarily removes material from the normal star formation cycle. This creates temporary gaps in gas availability that can affect stellar birth rates throughout the galaxy. Everything in space spins, and that spin has consequences. Angular momentum, the technical term for rotational motion, determines how material moves through galaxies. When galaxies interact gravitationally, they redistribute angular momentum like cosmic spinning tops, transferring their rotation. Angular momentum follows strict conservation laws in physics. The total amount of spin in a system can't just disappear. It gets transferred from one place to another. Galactic interactions shuffle angular momentum around like dealing cards. Gas clouds that lose angular momentum spiral inward toward the galactic center. Gas clouds that gain angular momentum migrate outward to larger orbits. The companion galaxy's gravitational influence determines which regions gain or lose rotational energy. This angular momentum redistribution creates the large-scale gas flows that fuel star formation in spiral arms. Without this gravitational stirring, gas would remain trapped in stable circular orbits. The interaction liberates material to participate in the ongoing stellar nursery activity. Gas doesn't flow randomly through the whirlpool. It follows organized traffic patterns created by density waves. These invisible gravitational waves sweep through the galaxy like cosmic traffic controllers, organizing the chaotic motion of individual gas clouds into coherent flow patterns. Density waves create alternating zones of compression and expansion as they propagate through the galactic disk. Gas flows into the compression zones, gets squeezed together, then flows out the other side. This creates a cosmic breathing pattern throughout the galaxy. The wave passage doesn't just compress gas, it also accelerates it. Gas clouds speed up as they flow into compression zones, then slow down as they exit. This creates systematic velocity patterns that astronomers can measure using radio telescopes. These organized flow patterns explain why star formation occurs preferentially along spiral arms. The density wave traffic control system delivers compressed gas exactly where stellar nurseries need raw material for building new stars. Galaxies contain vast magnetic fields that most people never consider. These invisible force fields stretch across thousands of light years, but they can't move through space on their own. They need gas to carry them along like cosmic hitchhikers. Magnetic field lines get frozen into moving gas clouds through electromagnetic interactions. When gas flows in new directions, it drags the magnetic field along for the ride. This process reshapes the galaxy's entire magnetic architecture over cosmic time. The dragging process works both ways. Moving gas distorts magnetic field lines, but magnetic forces also influence how gas flows through space. This creates feedback loops between gas motion and magnetic field structure throughout the galaxy. Magnetic field dragging helps channel gas flow along preferred directions. The magnetic forces act like cosmic guardrails, guiding gas streams along specific paths through the galactic disk. This magnetic channeling reinforces the spiral arm structure. Smooth galactic rotation gets disrupted when galaxies interact gravitationally. The orderly circular motion breaks down into chaotic, turbulent flows that inject random motion throughout both galactic systems. This turbulence fundamentally changes how gas behaves in the galaxy. Turbulence in space works like turbulence in Earth's atmosphere. Smooth flow breaks down into chaotic eddies and swirls. Gravitational interactions create the cosmic equivalent of atmospheric storms throughout the galactic disk. Turbulent motion increases the random velocity of gas clouds by factors of several compared to undisturbed galaxies. This extra kinetic energy affects everything from star formation rates to magnetic field structure. Turbulence becomes a major player in galactic evolution. The increased turbulence helps explain why interacting galaxies often display more active star formation than isolated systems. Turbulent compression can trigger star formation in gas clouds that would otherwise remain stable and inactive. Stars don't just produce light, they manufacture heavy elements through nuclear fusion in their cores. When massive stars explode as supernovas, they scatter these heavy elements throughout the galaxy. This creates a chemistry map showing where stellar evolution has been most active. Astronomers use the term metallicity to describe the abundance of heavy elements in gas and stars. Higher metallicity means more heavy elements. Lower metallicity means mostly just hydrogen and helium from the Big Bang. The galaxy displays a metallicity gradient. Heavy elements are most abundant near the center and become rarer toward the outer regions. This gradient reflects the history of star formation and element production throughout the galactic disk. Gravitational interactions can redistribute heavy elements by driving gas flows between different galactic regions. The companion galaxy's influence mixes material with different chemical compositions, gradually flattening the natural metallicity gradient over cosmic time. Active star formation in the Whirlpool comes with a hidden cost. It's rapidly consuming the galaxy's gas supply. Stars lock up gas in permanent stellar form, removing it from the reservoir available for future star formation. This creates a cosmic fuel crisis. Normal galaxies maintain a balance between gas consumption and gas replenishment. They form stars slowly enough that fresh gas from intergalactic space can partially refuel the stellar nurseries. The Whirlpool breaks this sustainable pattern completely. The enhanced star formation triggered by the galactic interaction consumes gas faster than it can be replaced. Current star formation rates would exhaust the available fuel supply within just a few 100 million years, a cosmic eye blink. This gas depletion process explains why starburst activity can't continue indefinitely. Eventually, the galaxy will run out of raw materials for making new stars. The spectacular stellar fireworks display we observe today represents a temporary cosmic celebration. The galaxy simultaneously pulls material inward toward its center while blasting processed material outward through stellar winds and supernova explosions. This creates a cosmic breathing pattern, inhalation and exhalation of galactic material operating on vast scales. Inflow processes bring fresh hydrogen gas from the outer regions and intergalactic space toward the central star formation regions. This material provides the raw fuel needed to maintain ongoing stellar nursery activity throughout the galactic disk. Outflow processes eject processed material enriched with heavy elements created by stellar nuclear fusion. Supernova explosions and stellar winds blow this chemically evolved gas back into intergalactic space at tremendous velocities. The balance between inflow and outflow determines the galaxy's long-term evolution. Too much inflow creates runaway star formation that quickly exhausts gas supplies. Too much outflow starves star formation by removing available fuel. The Whirlpool currently operates with inflow dominating, driving the enhanced stellar activity we observe today. At the heart of the Whirlpool lurks a gravitational monster so massive it defies imagination. This supermassive black hole contains the mass of millions of suns compressed into a region smaller than our solar system. Yet despite its incredible mass, it remains completely invisible to direct observation. Black holes earn their name because nothing can escape their gravitational pull, not even light itself. Once material falls past a certain boundary called the event horizon, it disappears forever from our universe. The black hole grows larger by consuming everything that ventures too close. Supermassive black holes occupy the centers of nearly all large galaxies. They formed during the early universe through processes that astronomers still don't fully understand. These cosmic monsters can contain anywhere from millions to billions of times our Sun's mass. The Whirlpool's central black hole has been sleeping quietly for most of the galaxy's history. But the ongoing gravitational interaction with its companion galaxy is beginning to wake this cosmic beast by feeding it fresh material. The central black hole has been starving for millions of years. Most of the time, very little material reaches the galactic center, where the black hole waits. But the companion galaxy's gravitational influence is changing this cosmic food delivery system dramatically. Normal galactic rotation keeps gas orbiting safely at large distances from the central black hole. The material follows stable circular paths that never bring it close enough to get consumed. This starvation diet keeps the black hole inactive and invisible. Gravitational interactions disrupt these stable orbits and create new pathways for gas to reach the galactic center. The companion's periodic gravitational steering drives material inward along spiral streams that eventually reach the black hole's neighborhood. This enhanced gas delivery is gradually awakening the sleeping monster. As more fuel becomes available, the central black hole begins to display signs of renewed activity after eons of dormancy. What happens when gas finally reaches a supermassive black hole? It doesn't fall straight in. It forms a spinning disk of superheated material that spirals slowly toward its doom. Astronomers call this structure an accretion disk, and it becomes one of the most energetic phenomena in the universe. The accretion disk forms because gas carries angular momentum, rotational motion that can't be easily destroyed. As material approaches the black hole, it must gradually lose this spin before it can fall in. This creates a traffic jam of rotating gas. Friction within the spinning disk heats the gas to millions of degrees. This superheated material glows brightly across the electromagnetic spectrum, making the previously invisible black hole suddenly detectable. The accretion disk becomes a cosmic lighthouse powered by gravitational energy. The disk doesn't just glow, it also launches high-speed jets of material from the black hole's poles. These jets can extend thousands of light-years into space, carrying energy and material far from the galactic center. You can't hear a black hole's heartbeat directly, but astronomers can detect it through subtle changes in the light coming from the galactic center. The Whirlpool displays what astronomers call LUNAR activity. That's technical jargon for low-ionization nuclear emission region. LUNAR emission comes from gas that's been gently heated by the black hole's radiation field. Unlike violent quasars that blast out tremendous energy, LUNAR galaxies show only mild central activity. Think of it as the difference between a roaring bonfire and glowing embers. This weak emission indicates the black hole is consuming material at a relatively modest rate. It's not gorging itself on cosmic fuel, but rather snacking steadily on the enhanced gas supply delivered by the gravitational interaction. LUNAR activity represents the early stages of black hole awakening. As more material reaches the galactic center, this gentle emission could potentially evolve into much more dramatic displays of black hole power. The hottest material in the galaxy radiates X-rays, the same high-energy radiation used in medical imaging, but millions of times more intense. X-ray telescopes pointed at the Whirlpool Center detect this telltale signature of superheated gas falling into the supermassive black hole. X-ray emission requires temperatures of millions of degrees. Normal stellar processes can't generate such extreme conditions. Only the intense gravitational fields near black holes can heat material to these incredible temperatures. The X-ray brightness varies over time as the feeding rate changes. When more gas reaches the black hole, X-ray emission increases. When the fuel supply diminishes, the emission fades. This variability proves the radiation comes from active accretion processes. Space-based X-ray observatories can penetrate the dust and gas that blocks visible light from the galactic center. This allows astronomers to study black hole feeding in real time, watching the cosmic monster consume its gravitationally delivered meals. Black holes don't just consume material, they also launch spectacular jets of high-speed particles into space. These cosmic searchlights extend thousands of light-years from the galactic center, carrying enormous amounts of energy far beyond the black hole's immediate neighborhood. The jets form when magnetic fields get twisted by the black hole's rotation. Charged particles get accelerated to nearly the speed of light and blasted outward along the black hole's rotational axis. This creates two opposing beams of material shooting into space. Jet formation requires specific conditions that don't always exist. The black hole must be actively feeding and rotating rapidly. The Whirlpool's jets remain relatively weak compared to more dramatic systems, but they're detectable with radio telescopes. These outflows can influence star formation throughout the galaxy by heating and dispersing gas clouds. The black hole's jets become a regulatory mechanism that can either trigger or suppress stellar nursery activity across vast regions of space. Black hole feeding isn't a steady process. It's chaotic and unpredictable. The brightness of the galactic center changes over time scales ranging from hours to years. This variability provides crucial clues about how supermassive black holes consume material. Variability occurs because the accretion process is inherently unstable. Gas doesn't flow smoothly into black holes. It gets disrupted by magnetic fields, turbulence, and gravitational instabilities. These disruptions create flickering patterns in the emitted radiation. Different wavelengths of light vary on different time scales. X-ray emission can change within hours, while optical light might vary over months. This multi-wavelength variability helps astronomers understand the structure and physics of accretion flows. The Whirlpool's central variability confirms that its black hole is actively consuming material delivered by the ongoing galactic interaction. A truly dormant black hole would show steady, unchanging emission patterns. Heavy elements concentrate near galactic centers like sediment settling in a cosmic river. These chemical fingerprints record the history of stellar evolution and black hole growth throughout the galaxy's lifetime. The central regions contain the richest concentrations of elements forged in stellar cores. Metallicity measures the abundance of elements heavier than hydrogen and helium. Stars manufacture these heavy elements through nuclear fusion, then distribute them through supernova explosions and stellar winds. Over cosmic time, this enriches the galactic center with processed material. The concentration gradient shows how material has flowed inward throughout the galaxy's evolution. Each generation of stars adds more heavy elements to the central reservoir. The current chemical composition reflects billions of years of stellar processing. black hole growth correlates with this chemical enrichment because both processes depend on the same gas flows that bring material toward the galactic center. The metallicity concentration provides an indirect measure of how much material has fed the central black hole over cosmic time. Active black holes create their own regulatory system through feedback processes that can either encourage or suppress nearby star formation. This cosmic thermostat prevents black holes from consuming all available material and helps explain why they don't grow indefinitely. Positive feedback occurs when black hole jets compress nearby gas clouds, triggering new rounds of star formation. The jets act like cosmic plows, creating dense regions where stellar nurseries can ignite. This process can temporarily increase the local star formation rate. Negative feedback happens when black hole activity heats surrounding gas so much that star formation shuts down completely. The heated gas becomes too hot and thin to collapse into new stars. This starves the black hole by reducing its long-term fuel supply. The balance between positive and negative feedback determines the galaxy's overall evolution. Currently, the Whirlpool shows signs of both processes operating simultaneously as the awakening black hole responds to its enhanced fuel delivery system. Many galaxies develop central bar structures, elongated concentrations of stars that act like cosmic conveyor belts transporting material toward the galactic center. These stellar highways provide the most efficient mechanism for feeding supermassive black holes. Central bars form when galaxies develop gravitational instabilities in their inner regions. The bar structure creates non-circular orbits that channel gas inward much more efficiently than normal spiral arms. Material follows the bar like cars following highway lanes. The Whirlpool shows evidence of a weak central bar that helps funnel gas toward its supermassive black hole. This bar structure developed partly in response to the gravitational perturbations from the companion galaxy. Bar-driven gas flows explain why many interacting galaxies display enhanced central activity. The gravitational stirring that creates tidal effects also promotes bar formation, which in turn provides efficient fuel delivery to central black holes. Black holes and galaxies grow together in a cosmic partnership that spans billions of years. The mass of a galaxy's central black hole correlates tightly with the mass of its central bulge of stars. This relationship reveals deep connections between black hole growth and galactic evolution. The correlation suggests that black holes and galaxies regulate each other's growth through feedback processes. Growing black holes influence star formation throughout their host galaxies. The growing galaxies provide fuel for their central black holes through gas and flows. This coevolution explains why supermassive black holes exist in nearly all large galaxies. The black holes aren't random additions. They're integral components that help shape galactic structure and evolution over cosmic time. The Whirlpool's ongoing interaction provides a laboratory for studying this coevolution in real time. The enhanced gas flows triggered by the galactic collision simultaneously feed the central black hole and boost star formation throughout the disk. We're witnessing cosmic coevolution in action. Charles Messier was obsessed with finding comets in 1773. These fuzzy celestial visitors brought fame and fortune to their discoverers. But fuzzy objects that didn't move frustrated comet hunters beyond measure. They were just annoying obstacles cluttering up the sky. Messier spotted object number 51 while scanning the constellation Canes Venatici. It looked exactly like a comet at first glance. But night after night, the fuzzy patch stayed in exactly the same position. No comet behaves this way. Rather than ignore this cosmic nuisance, Messier decided to catalog it. He created a list of non-comet objects that comet hunters should ignore. His nuisance list accidentally became the most famous deep sky catalog in astronomy. What seemed like a mere obstacle to comet discovery was actually one of the universe's most spectacular galactic systems. Messier's methodical record-keeping preserved the first scientific documentation of the cosmic masterpiece we now call the Whirlpool Galaxy. You couldn't see spiral structure in galaxies until someone built a telescope powerful enough to reveal it. Lord Rosse constructed a monster telescope with a 6-foot mirror in 1845, the largest in the world at that time. This engineering marvel could gather enough light to show details invisible to smaller instruments. Rosse pointed his giant telescope at Messier 51 and saw something unprecedented. The fuzzy blob wasn't uniform. It displayed a clear spiral pattern winding outward from the center. This was humanity's first glimpse of galactic architecture. The discovery revolutionized our understanding of cosmic structure. Those mysterious nebulae weren't just formless gas clouds. They were organized systems with definite patterns and structures. Rosse coined the term Whirlpool Nebula to describe the spiral pattern he observed. His detailed drawings showed 2 distinct spiral arms curving gracefully outward from a bright central region. These sketches became the first scientific documentation of spiral galaxy structure, launching an entirely new field of astronomical research. Human eyes can only see what's visible in the moment, but photographic plates can collect light for hours, revealing details completely invisible to direct observation. The introduction of photography transformed astronomy from a visual science into a precise, quantitative discipline. Long-exposure photographs of the Whirlpool revealed intricate details that visual observers had missed completely. The spiral arms showed complex structure with bright knots, dark lanes, and subtle color variations. Photographic plates captured information that human memory could never preserve accurately. Photography also enabled systematic surveys of the sky. Astronomers could photograph thousands of objects and study them at leisure in laboratory conditions. This mass production approach to astronomical discovery accelerated the pace of cosmic exploration dramatically. The Whirlpool became one of the most frequently photographed objects in the sky. Each new photographic technique revealed additional layers of structure and complexity in this galactic masterpiece. What if you could measure the speed of distant galaxies using nothing but their light? Spectroscopy makes this possible by analyzing how motion affects the colors of starlight. This technique revealed that the Whirlpool and its companion are locked in gravitational motion. Spectroscopy works by spreading starlight into its component colors, like a prism creating a rainbow. Moving objects shift these colors slightly. Approaching objects appear bluer, while receding objects appear redder. This Doppler effect allows astronomers to measure cosmic velocities. Spectroscopic observations of the Whirlpool showed that different parts of the galaxy move at different speeds. The systematic velocity patterns proved that galaxies rotate like enormous pinwheels spinning through space. The companion galaxy showed its own distinct motion pattern. These velocity measurements provided the first direct evidence that spiral nebulae were actually rotating galaxy systems far beyond our own Milky Way. Spectroscopy transformed fuzzy photographs into detailed maps of cosmic motion. Most of the universe remains invisible to optical telescopes. Cosmic dust blocks visible light, hiding vast regions of galactic structure from traditional observation. Radio astronomy opened a completely new window on the cosmos by detecting radiation that penetrates this cosmic fog. Radio telescopes detect emissions from hydrogen gas. the most abundant element in the universe. Hydrogen atoms emit radio waves at a specific frequency when their electrons flip between energy levels. These radio signals can travel through dust clouds that completely block optical light. Radio observations of the Whirlpool revealed the distribution of hydrogen gas throughout both galaxies. The radio maps showed spiral structure extending far beyond the visible edges of the system. Hidden gas reservoirs became visible for the first time. The 21-centimeter hydrogen line became astronomy's most important radio frequency. This invisible radiation revealed the true extent and structure of galactic systems throughout the universe, including details of the Whirlpool impossible to detect through optical observation. Stars form inside dense dust clouds that remain completely opaque to visible light. These stellar nurseries hide their activity behind cosmic veils that no optical telescope can penetrate. Infrared astronomy sees through these veils by detecting the heat signature of warm dust. Dust grains absorb ultraviolet light from nearby stars and re-emit this energy as infrared radiation. Infrared telescopes can detect this thermal glow and map dust distributions throughout galactic systems. What appears dark and empty in visible light blazes brightly in infrared images. Space-based infrared observatories like IRAS and Spitzer map the Whirlpool's dust structure in unprecedented detail. The infrared images revealed hidden star formation regions and traced the spiral arms through dust lanes invisible to optical observation. Infrared observations showed that star formation activity extends throughout the galaxy system, not just in the visible spiral arms. The thermal emission maps provided a complete census of stellar nursery activity across both galactic components. Earth's atmosphere blurs astronomical images like looking through constantly moving water. Even the best ground-based telescopes cannot achieve perfect focus because of atmospheric turbulence. The Hubble Space Telescope solved this problem by observing from above the atmosphere. Hubble's crystal-clear images of the Whirlpool revealed individual stars and star clusters throughout both galaxies. The Space Telescope could resolve details impossible to detect from Earth's surface. Each spiral arm showed intricate structure with bright stellar associations and dark dust lanes. The Space Telescope's ultraviolet sensitivity revealed hot young stars invisible to ground-based observation. Hubble mapped the star formation history of both galaxies by identifying stellar populations of different ages and compositions. Hubble's multi-wavelength capabilities allowed astronomers to study the Whirlpool across the entire electromagnetic spectrum. Each wavelength revealed different aspects of galactic structure and evolution, creating a comprehensive portrait of this cosmic system. The most violent processes in galaxies remain invisible to optical observation. Supernova explosions, black hole activity, and shock-heated gas emit primarily high-energy X-ray radiation. X-ray astronomy revealed an entirely different view of galactic systems. X-ray telescopes like Chandra and XMM Newton map the hot gas distribution throughout the Whirlpool system. These observations revealed shock-heated regions where gas flows collide at hundreds of kilometers per second. The X-ray emission traced the most energetic processes in both galaxies. Central X-ray sources revealed black hole activity in both galactic nuclei. The X-ray variability patterns provided evidence for active accretion processes feeding these supermassive black holes. This high-energy emission was completely undetectable by optical telescopes. X-ray observations showed that galactic interactions create cosmic violence on scales impossible to imagine. The collision between these galaxies generates temperatures of millions of degrees throughout vast regions of space. Single radio telescopes can't achieve the sharp focus needed to map detailed galactic structure, but networks of radio telescopes working together can create images sharper than any single instrument. This interferometry technique revolutionized radio astronomy. Radio interferometry works by combining signals from multiple telescopes separated by large distances. The technique creates virtual telescopes with effective sizes equal to the distance between individual antennas. Larger virtual telescopes produce sharper images. The Very Large Array and ALMA map the Whirlpool's gas motions with incredible precision. These radio interferometers traced molecular clouds, measured magnetic field structures, and followed gas flows throughout both galactic systems. Interferometric observations revealed the detailed mechanics of galactic interaction. The radio maps showed exactly how gravitational forces redistribute gas and trigger star formation throughout the collision zone. No single type of telescope can tell the complete story of galactic evolution. Different wavelengths reveal different aspects of cosmic structure and activity. Modern astronomy combines observations across the entire electromagnetic spectrum to create comprehensive galactic portraits. Each wavelength band reveals specific galactic components. Optical light shows stars, radio waves trace gas, infrared radiation maps dust, X-rays reveal hot plasma, ultraviolet emission identifies stellar nurseries. Combining these views creates complete galactic blueprints. Multi-wavelength studies of the Whirlpool revealed the complex interactions between stars, gas, dust, and magnetic fields throughout both galaxies. Each component influences the others in ways invisible to single wavelength observation. This synthetic approach transformed the Whirlpool from a pretty picture into a detailed case study of galactic physics. The multi-wavelength data provided the complete information needed to understand how galaxy interactions drive cosmic evolution. Modern supercomputers can recreate the entire Whirlpool interaction using the fundamental laws of physics. These numerical simulations follow the gravitational dance between galaxies across billions of years of cosmic time. The computed results match observations with remarkable accuracy. Simulation codes track millions of particles representing stars and gas clouds. Each particle feels gravitational forces from all other particles according to Newton's laws. Supercomputers calculate these interactions through cosmic time to predict galactic evolution. The simulations revealed details impossible to observe directly. They showed how the interaction began, how it evolved over cosmic time, and how it will continue into the future. The computed galaxy models look virtually identical to telescopic observations. Numerical simulations prove that gravity alone can explain the spectacular structure we observe. The match between computed models and real observations validates our understanding of galactic physics and cosmic evolution. The newest space telescope sees deeper into cosmic history than any previous instrument. The James Webb Space Telescope observes in infrared wavelengths that penetrate cosmic dust and reveal hidden stellar nurseries. Its unprecedented sensitivity opens entirely new frontiers in galactic astronomy. Webb's infrared vision can see through the dust lanes that block optical observation. The Space Telescope maps star formation activity throughout the Whirlpool system with incredible detail. Each stellar nursery appears as a bright infrared source surrounded by glowing dust. The telescope's spectroscopic capabilities can analyze the chemical composition of gas clouds throughout both galaxies. These measurements reveal how stellar evolution has enriched different regions with heavy elements over cosmic time. Webb represents the culmination of centuries of technological development in astronomical observation. From Messier's visual discoveries to space-age infrared imaging, each advance revealed new layers of cosmic complexity in this galactic masterpiece. Every orbit in the universe slowly shrinks over time. The companion galaxy can't circle its larger partner forever. Physics demands that this cosmic dance must eventually end. Two invisible forces are gradually stealing energy from the orbital motion, causing the galaxies to spiral inexorably toward their final merger. Gravitational wave radiation carries energy away from any accelerating massive object. As the companion orbits the main galaxy, it constantly accelerates due to changing direction. This acceleration creates ripples in space-time itself that propagate outward at the speed of light, carrying orbital energy into the cosmos. Dynamical friction provides the second energy drain. The companion galaxy plows through a sea of dark matter and scattered stars surrounding the main galaxy. This cosmic drag force acts like atmospheric friction, slowing down a satellite, gradually reducing the orbital velocity. Both processes operate so slowly that billions of years pass between noticeable changes. But cosmic time is patient, and these invisible forces will eventually force the two galaxies into a catastrophic final embrace that will reshape both systems beyond recognition. When galaxies finally merge, they don't smash together like cosmic car crashes. Instead, they perform an elegant gravitational ballet that transforms two separate systems into one magnificent elliptical galaxy. The merger process unfolds over hundreds of millions of years through a series of increasingly dramatic orbital encounters. The first close passage disrupts both galactic structures through powerful tidal forces. Spiral arms get stretched and distorted. Star formation rates spike dramatically as gas clouds collide and compress. The galaxies emerge from this encounter visibly changed, but still recognizably separate. Subsequent passages become progressively more violent as orbital energy dissipates. Each encounter strips away more material and further distorts the galactic structures. The systematic loss of orbital angular momentum inevitably drives the galaxies toward their final coalescence. The ultimate merger occurs when the galactic centers finally unite into a single gravitational system. This cosmic wedding ceremony transforms the beautiful spiral architecture into a smooth elliptical galaxy, a completely different type of cosmic citizen with its own distinct characteristics and evolution. Imagine shuffling a deck of cards so thoroughly that no two cards retain their original relationship. Galactic mergers perform the same cosmic shuffling with billions of stars, completely randomizing their orbits through chaotic gravitational interactions that destroy all traces of the original spiral structure. During the merger process, stars don't collide directly. Space is too vast for actual stellar crashes. Instead, they experience close gravitational encounters that dramatically alter their orbital paths. Stars that once followed orderly circular orbits get scattered into random elliptical trajectories. The gravitational chaos operates through what physicists call the three-body problem. When three or more massive objects interact gravitationally, their motions become unpredictable and chaotic. Galactic mergers create billions of simultaneous three-body interactions throughout both systems. This stellar scrambling erases the organized spiral structure that took billions of years to develop. The beautiful cosmic pinwheel transforms into a featureless elliptical galaxy where stars follow random orbits with no preferred direction or pattern. The most dramatic event in the entire merger process happens at the very end, when two supermassive black holes spiral together and unite in a cosmic collision that shakes the fabric of space-time itself. This black hole merger represents the ultimate gravitational catastrophe. a collision so violent it sends ripples throughout the universe. Black hole mergers don't happen instantly. The two gravitational monsters must overcome enormous angular momentum barriers before they can unite. They spiral closer together over millions of years, orbiting each other at ever-increasing speeds as their separation shrinks. The final moments generate gravitational waves so powerful they can be detected by instruments on Earth. When black holes containing millions of solar masses merge, they convert enormous amounts of mass directly into gravitational wave energy according to Einstein's famous equation. The merged black hole will contain slightly less mass than the original pair combined. The missing mass gets converted into gravitational wave energy that propagates throughout the cosmos at light speed, carrying the news of this cosmic catastrophe to distant civilizations. What happens when a galaxy runs out of fuel for making new stars? The spectacular starburst activity that makes the Whirlpool so brilliant today cannot continue indefinitely. Eventually, the enhanced star formation will consume all available gas, bringing the cosmic fireworks display to a quiet end. Starburst galaxies consume their gas supplies at unsustainable rates. Normal galaxies form stars slowly enough that fresh gas from intergalactic space can partially replenish their stellar nurseries. But interacting galaxies like the Whirlpool burn through fuel faster than it can be replaced. The star formation shutdown happens gradually as gas supplies dwindle. Stellar nurseries begin failing when local gas densities drop below critical thresholds. The brilliant blue light from massive young stars fades as fewer new stars form to replace those that burn out. The post-merger galaxy will glow with the warm yellow light of older stars, the long-lived stellar citizens that survived the transition from spiral to elliptical structure. The age of active star formation will end, replaced by a quieter phase of galactic evolution. Not every star survives the galactic merger process. Gravitational chaos during the final coalescence launches some unlucky stars into intergalactic space at tremendous velocities, condemning them to wander the cosmic wilderness forever as lonely refugees from their destroyed home galaxies. Stellar ejection occurs through gravitational slingshot encounters near the merged galactic center. When a star approaches the supermassive black hole binary system, it can receive a tremendous gravitational kick that accelerates it beyond the galaxy's escape velocity. These hypervelocity stars race through intergalactic space at speeds of thousands of kilometers per second. They carry no companions and have no hope of ever finding another galactic home. They become permanent nomads in the vast emptiness between galaxy clusters. Astronomers have discovered hypervelocity stars in our own cosmic neighborhood, lone stellar wanderers that were likely ejected from galactic mergers in the distant past. These cosmic refugees provide direct evidence that galaxy mergers routinely exile some of their stellar citizens. After billions of years of violent interaction, what remains of two beautiful spiral galaxies? The merger remnant will be a giant elliptical galaxy, a completely different type of cosmic citizen with smooth, featureless structure and no ongoing star formation activity. Elliptical galaxies represent the endpoint of galactic evolution. They contain mostly old, red stars following random orbits with no organized pattern. The spectacular spiral arms, active star formation regions, and organized rotation of the original galaxies disappear completely. The remnant will be significantly larger than either original galaxy. Mergers redistribute stellar material across much larger volumes, creating puffy, extended structures. The combined system occupies more space than the sum of its original components. This transformation from spiral to elliptical represents one of the fundamental evolutionary pathways in cosmic history. Many of the giant elliptical galaxies we observe today likely formed through similar merger processes in the distant past. Imagine astronomers on distant planets watching this merger unfold over cosmic time. The spectacular spiral structure that makes the Whirlpool famous today will gradually disappear, replaced by an increasingly distorted and chaotic appearance that eventually settles into smooth elliptical symmetry. The most obvious change will be the loss of spiral arm definition. The sharp, well-defined arms visible today will become increasingly disrupted with each orbital passage. Tidal tails and bridges will stretch between the galaxies as material gets gravitationally redistributed. Color changes will accompany structural evolution. The brilliant blue light from active star formation regions will fade as gas supplies get exhausted. The galaxy will redden as older stellar populations dominate the total light output. Size and brightness will also evolve dramatically. The combined system will appear larger but dimmer than today as stellar material spreads across greater volumes. Future observers will see a completely different object occupying the same region of sky. How long does it take to completely destroy two spiral galaxies? The entire merger process unfolds over approximately 5 billion years. Longer than Earth has existed, but still just a brief moment in cosmic history. This timeline gives us perspective on the vast scales involved in galactic evolution. The merger timeline divides into distinct phases with different characteristics and durations. The initial approach and first tidal disruption occur over the first billion years. Multiple orbital passages and increasing interaction dominate the next 3 billion years. The final coalescence and black hole merger happen relatively quickly during the last billion years of the process. Once the galactic centers merge, the remaining structural evolution proceeds rapidly by cosmic standards. This 5 billion year time scale means that civilizations like humanity could witness only tiny fractions of the complete process. The merger that began before Earth formed will continue long after our sun burns out. The Whirlpool merger tells the story of our own galactic destiny. In approximately 4 billion years, our Milky Way will collide with the Andromeda Galaxy in a cosmic collision that mirrors the Whirlpool interaction we observe today. We're watching our own future unfold in distant space. The Milky Way and Andromeda are approaching each other at hundreds of kilometers per second. This collision course was set billions of years ago by the gravitational attraction between the two most massive galaxies in our local cosmic neighborhood. Computer simulations of the Milky Way-Andromeda merger predict outcomes similar to the Whirlpool system. Our beautiful spiral galaxy will eventually transform into an elliptical system that astronomers have nicknamed Milkomeda, a blend of the two original galaxy names. Studying the Whirlpool interaction provides crucial insights into this future cosmic catastrophe. The physics governing galactic mergers operates identically throughout the universe, making the Whirlpool a perfect laboratory for understanding our own galactic destiny written in the stars.